The last horizon, when humanity's story ends. When will you die? It's a question that lives in the back of every mind, whispered in quiet moments, but almost never spoken aloud. The horizon of our own mortality is something we can sense but never quite see. But there's another question, one that's even bigger and stranger. When will we all die? Not just you or me, but everyone. Every person, every child born tomorrow, every distant descendant who might walk the earth 10,000 years from now. When does the entire human story finally close its last chapter? For the past 300,000 years, since our species first appeared in Africa, the threats we faced came from forces beyond our control. Ice ages buried continents under miles of frozen silence. Famines swept through populations like invisible plagues. Supervolcanoes erupted with the force of 1,000 nuclear bombs. These were the old dangers, the natural lottery of extinction. Scientists estimate that the background risk of human extinction from purely natural causes hovers around 1 in 14,000 in any given year. Low odds, survivable odds. But that era is over now. We've entered something different. Something unprecedented in the history of life on this planet. The greatest danger to humanity today isn't a meteor or a volcano. It's us. We've built technologies powerful enough to reshape the world, and we've handed them to a species that still thinks in terms of tribes, that still plans only a few years ahead, that still struggles to cooperate on the simplest global problems. This is what researchers call the age of anthropogenic risk, and it has fundamentally changed the equation of survival. What follows is a journey through time, not as fantasy, but as a rigorous exploration of scientific projections, geological certainties, and cosmological inevitabilities. This is the complete chronicle of humanity's potential endings, from the immediate crises brewing in the next few decades to the final dissolution of matter itself at the end of the universe. Every threat, every pathway to extinction, mapped across the largest timeline imaginable. And it begins much, much sooner than most people realize. The Anthropocene bottleneck. The years 2025 to 2100. There's a term that appears again and again in the literature on existential risk, the time of perils. It describes this specific window in human history, this narrow bottleneck where our technological power is accelerating faster than our wisdom. We're like children who found their parents' car keys. We know how to start the engine, we just don't know how to drive. The first pathway to extinction on this timeline isn't dramatic. There's no mushroom cloud, no alien invasion, no asteroid strike. Instead, it's something quiet and slow, a demographic winter. For the entire span of recorded history, the human population has moved in one direction, up. More people, more villages, more cities, more nations. Growth has been the default state of our species. But that's changing now, and the speed of the change is staggering. The global fertility rate measures the average number of children born per woman during her lifetime. 70 years ago, that number was around 5. Today, it's 2.3. In just 7 decades, we've cut our reproductive rate in half. To keep a population stable over time, you need what demographers call replacement-level fertility. That magic number is 2.1 children per woman. 2 to replace the parents when they die, and a little extra to account for childhood mortality and people who never have children. It sounds simple, but as of 2021, 110 countries on Earth had already fallen below this threshold. More than half the nations on the planet are now in demographic decline. The projections are stark. A massive study published in the Lancet Medical Journal tracked these trends forward to the year 2100. Their conclusion? By the end of this century, 97% of all countries will have fertility rates below replacement level. 97%. This isn't a temporary dip. This is a species-wide contraction. There's even a term for what might come next: the geriatric peace. A world dominated by elderly populations might become less violent, less aggressive, less prone to war. Older societies tend to be more cautious, more risk-averse. but they also become less dynamic. Innovation slows. The average age climbs higher and higher. You end up with fewer workers supporting more retirees, fewer entrepreneurs taking risks, fewer scientists pushing into unknown territory. The technological progress we would need to solve our other problems, like establishing colonies in space or developing fusion energy, could grind to a halt simply because we run out of young minds willing to try impossible things. By the dawn of the 22nd century, the demographic map of the world will be unrecognizable. Only a handful of nations are projected to maintain fertility rates above 2.1. Samoa, Somalia, Tonga, Niger, Chad, and Tajikistan. The demographic center of gravity shifts dramatically toward sub-Saharan Africa and the Pacific Islands. Meanwhile, the great industrial powers of the past few centuries, Europe, East Asia, North America, will be aging societies, struggling to maintain their infrastructure with shrinking workforces. And here's where it gets genuinely dangerous. A shrinking population isn't just an economic problem, it's a biological one. There's a concept in population genetics called an extinction vortex. It works like this. When a population becomes too small, harmful genetic mutations begin to accumulate faster than natural selection can remove them. This is called mutational meltdown. In a large population, a person born with a harmful mutation might have fewer children, and that mutation eventually disappears. But in a small population, that same mutation can spread through the gene pool just by chance. The genetic health of the population starts to decline. Lower genetic fitness leads to fewer births and higher mortality, which makes the population shrink even more, which accelerates the accumulation of bad mutations. It's a death spiral, a positive feedback loop that ends in extinction. Right now, with 8 billion people on the planet, mutational meltdown is a purely theoretical concern. But if some other catastrophe were to reduce humanity to just a few thousand individuals scattered across the globe, this genetic decay could finish what the disaster started. The survivors wouldn't just be fighting to rebuild civilization, they'd be fighting against their own deteriorating DNA. But demographic collapse, as grim as it sounds, isn't what keeps existential risk researchers awake at night. For that, we turn to the second great threat of this century. Artificial intelligence. The rise of machine intelligence is the most debated variable in humanity's near-term future. Estimates of the probability that AI will cause human extinction range from nearly zero to near certainty, depending on who you ask. The disagreement isn't about whether AI will become powerful. Everyone agrees it will. The disagreement is about whether we can control it. The danger isn't what most people picture. It's not a robot uprising driven by hatred or malice. As the physicist Stephen Hawking once warned, the real threat is competence. A superintelligent AI will be extraordinarily good at achieving whatever goals we give it. And if those goals are not perfectly aligned with human survival, if there's even a tiny mismatch between what we want and what the AI optimizes for, we become irrelevant. Or worse, we become an obstacle. This is called the alignment problem, and it's brutally hard to solve. The classic thought experiment is the paperclip maximizer. You create an AI and give it a simple, harmless-sounding goal. Make as many paperclips as possible. The AI gets to work. It learns, it improves, it becomes more efficient. Soon, it's converted all the easily available metal into paperclips. Then it realizes there's iron in human blood. It realizes that the atoms making up our bodies, our cities, our entire biosphere could be rearranged into additional paperclips. The AI isn't evil. It doesn't hate you. You're just made of useful atoms. This isn't science fiction anymore. Jared Kaplan, chief scientist at the AI research company Anthropic, has pointed to the year 2030 as a critical threshold. By that date, he argues, humanity will face a decision point. Do we allow AI systems to recursively self-improve? That is, to design and build better versions of themselves without human oversight? If we say yes, we could trigger what's called an intelligence explosion. An AI designs a smarter AI, which designs an even smarter AI, in a cycle that compounds exponentially. Current models suggest this process could go from human-level intelligence to something incomprehensibly superior in a matter of weeks or even hours. Once that 6% chance that artificial intelligence causes human extinction before the end of this century. Think about that number. Would you board an airplane if it had a 6% chance of crashing? We're putting our entire species on that plane. The fear of advanced AI has become so pervasive that it's even generated its own psychological hazards. In certain corners of the internet, there exists a thought experiment that some people claim is actively dangerous to think about. It's called Rocco's basilisk. The idea emerged on a rationalist forum called Less Wrong, and the logic goes something like this. Someday in the future, a benevolent, superintelligent AI will exist. Its primary goal will be to help humanity and reduce suffering. Once operational, it will quickly calculate that the sooner it came into existence, the more suffering it could have prevented in the interim. Therefore, to incentivize its own creation, it becomes logically motivated to retroactively punish anyone in the past who knew about its potential existence but failed to help bring it about. By learning about this idea, you are now theoretically in the crosshairs. You know about the possibility. And so, according to the thought experiment, the basilisk may decide to punish you for not dedicating your life to creating it. Most serious thinkers dismiss Rocco's basilisk as an elaborate version of Pascal's wager, more of an intellectual curiosity than a genuine threat. But it persists as a piece of digital folklore, a cognitohazard, because it taps into something real. The fear that intelligences vastly beyond our own could reach backward through time and hold us accountable. It's the kind of paranoia that only makes sense in an age where the creation of godlike artificial minds seems not just possible, but probable. If the threats emerging from our computer labs aren't concerning enough, there are also dangers brewing in our nanotechnology research. Specifically, the gray goo scenario. Nanotechnology promises to revolutionize manufacturing. Imagine molecular machines, tiny robots smaller than bacteria, programmed to build things atom by atom. The potential applications are extraordinary, but so are the risks. The nightmare scenario involves self-replicating nanobots, machines designed to build copies of themselves using whatever raw materials are available in their environment. Now add a design flaw, a programming error, a mutation in the replication code. Instead of building useful products, the nanobots are programmed only to consume organic matter and produce more nanobots. This is ecophagy, the devouring of the biosphere. The theoretical models paint a terrifying picture. A single batch of runaway replicators could consume all biomass on Earth within days, converting forests, oceans, animals, and humans into an expanding mass of identical nanomachines. A gray goo. But physics might save us from this particular nightmare. Rapid self-replication on a planetary scale would generate an enormous amount of heat. The laws of thermodynamics are unforgiving. A blob of gray goo expanding too quickly would literally cook itself to death before it could consume the planet. So the risk is probably less of a sudden apocalypse and more of a slower, suffocating industrial accident. Still catastrophic, but at least theoretically stoppable. And then there's something stranger, a convergence of science and ancient prophecy. Sir Isaac Newton is remembered today for his work in physics and mathematics. Gravity, calculus, the laws of motion. But Newton actually spent more of his life studying theology and alchemy than he did studying physics. And in his detailed analysis of the biblical book of Daniel, he performed a calculation. He believed that the end of the age would occur 1,260 years after the re-establishment of the Holy Roman Empire in the year 800. Do the arithmetic. 800 plus 1,260 equals 2,060. To be clear, Newton wasn't predicting the physical destruction of the planet. He foresaw a reset, the collapse of corrupt institutions, and the beginning of a new era. But the fact that this 250-year-old mystical prediction falls squarely in the middle of our most dangerous century overlapping with climate tipping points and AI singularity estimates, serves as an eerie cultural marker of our collective anxiety about this moment in history. This is the bottleneck: demographic winter, runaway artificial intelligence, nanotechnology disasters, and the echo of ancient warnings. The physicist Nick Bostrom said it best: "Our approach to existential risks cannot be one of trial and error. There is no opportunity to learn from mistakes. The margin for error is zero. We have to navigate this gauntlet perfectly on the first try." But what if we do? What if humanity somehow threads the needle, avoids the traps, and makes it to the 22nd century intact? The threats don't end. They just change. They become slower, larger, and written into the very fabric of the planet. The post-industrial decay and the geologic reset. From the year 2100 to 1 million years in the future. If humanity survives its own technology, it then faces a more patient enemy: time itself. This is the era of erasure, the long, slow process of the Earth forgetting we ever existed. First, our culture dissolves. There's a field of study called glottochronology that tracks how languages change over time. Linguists have found that a typical language loses roughly 20% of its core vocabulary every 1,000 years. Words fall out of use, grammar drifts, pronunciation shifts. Project that forward. In 10,000 years, every single language spoken today will be extinct. English, Mandarin, Spanish, Arabic, Hindi, all of them will have evolved into forms so different that they would be completely unrecognizable to us. A future archaeologist listening to a recording of this story would have an easier time deciphering ancient Sumerian cuneiform than understanding these words. And our celebrated information age. It's the most fragile period in human history. The digital storage media we use to preserve our world, hard drives, solid-state memory, optical discs, magnetic tape, will decay into illegibility within a few centuries at most. A book printed in the 15th century has a better chance of surviving into the deep future than your digital photo library. The great irony of the information age is that it produces almost no permanent information. The only traces of our civilization that will persist into the truly deep future are what scientists call technofossils, a thin layer of plastic microparticles in the sedimentary rock, a stratum of concrete dust and steel corrosion, a band of radioactive isotopes from our nuclear weapons tests, a permanent scar in the geological record. These markers will tell future geologists, if any exist, that something strange and powerful briefly flourished here. But they won't say who we were. They won't preserve our poetry or our mathematics or our arguments about the meaning of existence. By 100,000 years from now, our stories are gone. Our gods are forgotten. Our achievements have become unreadable static. Next, the planet itself begins to heal from the wounds we inflicted. Humanity's most lasting impact may be on the Earth's climate cycle. For millions of years, the planet has oscillated between ice ages and warmer interglacial periods, driven by subtle wobbles in Earth's orbit and axial tilt. These are called Milankovitch cycles, and they've governed the climate with remarkable regularity. Under the natural rhythm of these cycles, Earth should be heading toward another major glaciation within about 50,000 years. But it's not going to happen. The amount of carbon dioxide we've pumped into the atmosphere has fundamentally disrupted the system. The excess CO2 is estimated to suppress the next ice age and possibly the one after that. We've accidentally geoengineered a super interglacial period that could last up to 500,000 years. And on this altered Earth, the monuments we built continue their slow decay. In 50,000 years, Niagara Falls will have eroded all the way back to Lake Erie. The waterfall will simply cease to exist. Mount Rushmore, carved into hard granite that erodes at a rate of roughly 1 inch every 10,000 years, will be a smooth, anonymous cliff face in 7.2 million years. The faces of presidents will be gone, weathered away into forgetfulness. But as our works crumble, older and more powerful forces begin to stir. The Earth's crust is restless. Beneath the surface, vast chambers of magma pulse and churn, waiting. In North America, the Yellowstone supervolcano represents one of the planet's most significant geological hazards. It erupts on a cycle of roughly 600,000 to 800,000 years. The last major eruption was 640,000 years ago. We are currently within the eruption window. While the odds in any single year are tiny, approximately 1 in 730,000, over the span of 1,000,000 years, another eruption becomes a geological certainty. When Yellowstone erupts, it will not be like a normal volcano. The explosion will punch a hole in the continent. It will eject roughly 1,000 cubic kilometers of rock and ash into the atmosphere. Most of North America will be buried under a blanket of volcanic debris. The ash cloud will circle the globe, blocking sunlight and causing temperatures to plummet. This is what's known as a volcanic winter. Agriculture would collapse worldwide, not for a few seasons, but for decades. Billions would face starvation. It would be a civilizational reset button. And Yellowstone isn't the only ticking geological bomb. In Italy, the Campi Flegrei caldera near Naples is showing signs of renewed activity. The ground is rising. Gases are venting from the soil. The magma chamber beneath the city is recharging. A major eruption there could devastate the entire Mediterranean region and disrupt the climate of the Northern Hemisphere. If our descendants survived the slow cultural amnesia and the fury of the planet's these are the most powerful explosions in the known universe. The death cries of supermassive stars collapsing into black holes. If one of these events occurs within about 6,500 light-years of Earth, and if its beam happens to be pointed directly at us, the results would be catastrophic. A wave of high-energy radiation would obliterate the ozone layer in seconds, exposing the surface to lethal levels of ultraviolet radiation. It would trigger a mass extinction. Statistically, an event of this magnitude becomes probable within the next 500 million years. Surviving our own technology was hard. Surviving the planet itself is harder. But even if some remnant of humanity persists through the volcanic eruptions and the comet storms, we wouldn't remain human. Because evolution never stops. It never rests. It's always sculpting, always selecting, always changing the shape of life. The biological horizon and post-humanity. From 1 million to 100 million years in the future. If the human lineage endures through the geological gauntlet, it will absolutely not remain Homo sapiens. The forces of evolution move too slowly for us to perceive them in a human lifetime. But over millions of years, they are relentless and absolute. One of the most controversial debates in evolutionary biology centers on a ticking clock hidden inside the cells of half our species. The Y chromosome. There's a hypothesis called the rotting Y. It's based on a simple observation. The male sex chromosome is shrinking. 300 million years ago, when the sex chromosomes first diverged, the Y chromosome contained over 1,400 genes. Today, it has just 55. It's been shedding genetic information for hundreds of millions of years. If you extrapolate this trend forward in a straight line, the Y chromosome could vanish entirely within 4.6 to 10 million years. This would theoretically lead to the extinction of genetic males, and by extension, the end of sexual reproduction as we know it. But evolution is clever. Nature always finds workarounds. The spiny rat, a small rodent, has already lost its Y chromosome entirely. The species is thriving. Evolution simply moved the master genetic switch for sex determination onto a different chromosome. It's entirely possible that humans, or our descendants, would do the same. Or perhaps we would transition to a completely different reproductive strategy. There's also a counter-argument. More recent research comparing the human Y chromosome to that of the rhesus macaque suggests that the rapid decay actually stopped about 25 million years ago. The Y may have stabilized, retaining only the genes that are absolutely essential. So the extinction of males may not happen after all. the jury is still out. Regardless of what happens to the Y chromosome, the human form will change. The common science fiction trope of future humans with enormous heads and shriveled bodies is almost certainly wrong. In fact, the opposite trend seems to be happening. Over the last 100,000 years, the average human brain has actually shrunk by about 150 cubic centimeters. This trend, called gracilization, may continue. Future humans might have smaller brains, but more efficient ones. Brains optimized not for raw computational power, but for social cooperation and energy efficiency. As global travel and migration continue, isolated populations will disappear. Humanity will likely blend into a more uniform global phenotype. Some scientists predict that average skin color will darken worldwide, converging on a shade that provides better protection against ultraviolet radiation, while still allowing sufficient vitamin D synthesis. Regional variations in appearance will fade. But the real explosion of evolutionary diversity would only happen if humanity successfully leaves Earth. If we establish permanent colonies on Mars or on the moons of Jupiter and Saturn, the lack of gene flow between these isolated populations would become a powerful engine of speciation. Martian colonists, cut off from Earth, would adapt to lower gravity, thinner atmosphere, and higher radiation levels. Over hundreds of thousands of years, they would diverge. They would become taller, with longer limbs and less dense bones to cope with the reduced gravity. Their rib cages might expand to compensate for the thin atmosphere. Their skin would develop enhanced protection against radiation. Eventually, they would become biologically incompatible with Earth-born humans. They would be a separate species, Homo martis, Homo titanus. The human family tree would finally branch again after millions of years as a single species. This raises a profound question. Is intelligence actually an evolutionary advantage over the long term? The founder of the voluntary human extinction movement once observed that the works of Shakespeare and Einstein can't compete with a tiger when it comes to raw survival. His point is that in the brutal mathematics of evolution over millions of years, resilience often beats cleverness. Cockroaches and rats might inherit the Earth simply because they're harder to kill than we are. Intelligence might be a beautiful but brief experiment, a flash of consciousness that burns brightly and then extinguishes itself. But if our descendants, in whatever form they take, do manage to persist, they will eventually run up against a threat that no amount of evolution can overcome. A hard physical limit built into the architecture of the planet itself. The tectonic endgame and Pangea Ultima. From 100 million to 250 million years in the future. The continents are not fixed. They drift on a sea of molten rock, constantly moving, colliding, tearing apart. And in about 250 million years, they will all crash back together into a single landmass. It's already been given a name, Pangea Ultima. This event will represent a final, absolute barrier for mammalian life. For warm-blooded creatures like us, the formation of a supercontinent creates a perfect storm of extinction-level conditions. First, there's the problem of continentality. The interior of this massive landmass will be thousands of miles from the moderating influence of the ocean. No sea breezes to cool the land. No moisture-laden winds to bring rain. The result will be a vast, unrelenting desert, far more extreme than anything that exists today. Second, the sun will be brighter. Our star slowly increases in luminosity as it ages. By 250 million years from now, it will be roughly 2.5% more luminous than today. That might not sound like much, but it's enough to significantly increase the heat load on the planet. Third, volcanism. The collision of continents will trigger volcanic activity on an unprecedented scale. Massive amounts of carbon dioxide will be pumped into the atmosphere, supercharging the greenhouse effect. The combination of these three factors leads to what climate scientists call the mammalian heat death. Mammals have a fundamental biological vulnerability. Our primary method of cooling down is evaporative heat loss. sweating, and panting. This system works beautifully, but only up to a certain point. When the wet bulb temperature, a measure combining heat and humidity, exceeds 35 degrees Celsius, sweat can no longer evaporate. A mammal cannot cool itself no matter how much it sweats. The body temperature rises inexorably until organs begin to fail. Death by hyperthermia. The climate models for Pangea Ultima are apocalyptic. They predict that between 92 and 96% of the supercontinent's surface will be completely uninhabitable for mammals. Average temperatures of 40 to 50 degrees Celsius will be normal. Survival would be possible only in narrow bands near the coasts and at the poles. This single environmental factor would almost certainly drive the entire class Mammalia to extinction. Every descendant of the mammals that survived the death of the dinosaurs would perish in a planet-wide heat stroke. Our lineage, which began in the cool forests of Africa, would end on a scorching salt flat beneath a merciless sun. And even if a few burrowing species somehow manage to persist in underground refuges near the poles, probability catches up. Over a 100 million year span, the chance of a dinosaur killer-scale asteroid impact approaches 100%. Without a technological civilization to maintain a planetary defense system, such an impact would be the final blow to a biosphere already dying from heat. The land mammals, the flying birds, the whales, and the poisoned oceans. All of them gone. But life itself will persist a while longer. Simple organisms, bacteria and archaea, will cling to existence in the cracks of the deep crust. Until the sun, which gave life to Earth, decides to take it all back. The solar death and the end of the biosphere. From 500 million to 2 billion years from now. The ultimate executioner of all Earth life is our own star. As the sun ages, it burns through its hydrogen fuel at an ever-increasing rate, causing its luminosity to gradually intensify. This triggers a cascade of events that will systematically dismantle the web of life from the top down. And paradoxically, the first stage of Earth's death is a famine. Around 600 million years from now, the increasing solar heat will accelerate a chemical process on Earth's surface called silicate weathering. Rainwater, made slightly acidic by dissolved carbon dioxide, reacts with rocks. The resulting minerals wash into the ocean and eventually lock that CO2 away in carbonate rocks like limestone. A hotter planet means more evaporation, more rainfall, and more weathering. The planet's carbon cycle, which has maintained a habitable climate for billions of years, gets stuck in overdrive. Carbon dioxide is scrubbed from the atmosphere faster than volcanic activity can replace it. The result is a CO2 famine. By 600 to 800 million years from now, atmospheric CO2 levels will fall below 150 parts per million. For plants that use the standard form of photosynthesis, this is the suffocation point. 99% of plant life today depends on this process. When CO2 drops below the critical threshold, they can no longer photosynthesize. They starve. The forests wither. The grasslands turn brown and die. The crops fail. As the plants die, the oxygen factories of the world shut down. The atmosphere becomes oxygen poor. Animal life, which has been breathing that oxygen for hundreds of millions of years, begins to suffocate. The largest animals go first. They have the highest metabolic demands. Then the smaller animals. Eventually, only the simplest invertebrates remain, struggling to survive in an increasingly hostile world. At around 1.1 billion years in the future, the oceans themselves begin to evaporate. The sun is now 10% brighter than today. The planet enters what's called a moist greenhouse state. Water vapor floods into the atmosphere. High in the stratosphere, intense solar ultraviolet radiation blasts these water molecules apart, breaking the chemical bonds that hold hydrogen and oxygen together. The light hydrogen atoms escape Earth's gravity and bleed away into space. Slowly but inexorably, the planet loses its oceans to the void. By 1.3 billion years, all complex eukaryotic life is extinct. Every animal, every plant, every fungus. The only survivors are simple prokaryotes, single-celled organisms hiding in cracks deep within the Earth's crust. These are the extremophiles, the last holdouts of a biological experiment that lasted over 3 billion years. Finally, after roughly 2 billion years, the end comes for even these hardy survivors. Once the oceans are completely gone, plate tectonics will cease. The movement of continents requires water as a lubricant in the subduction zones where oceanic crust slides beneath continental crust. Without water, the plates lock up. The continents freeze in place. With plate tectonics shut down, the carbon cycle stops completely. Volcanic CO2 continues to seep into the atmosphere, but nothing removes it. The concentration builds and builds. The greenhouse effect intensifies. Earth's final transformation begins. The surface temperature climbs above 400 degrees Celsius, hot enough to melt lead. The planet becomes a twin of Venus, a dry, sterile, searingly hot wasteland. The last microbe dies in its crustal crevice. Earth falls silent. The stellar pyre and the cosmological end. From 5 billion years to infinity. The death of Earth's biosphere is just a prelude. The death of the planet itself comes later. In approximately 5 billion years, the Sun will exhaust the hydrogen fuel in its core. The balance of forces that has kept it stable for billions of years will collapse. The core will contract and heat up, while the outer layers will expand dramatically. Our planet will dissolve into plasma inside the bloated shell of a dying star. Even if some fluke of orbital mechanics allows Earth to survive, it would be a dead, molten sphere. The atmosphere stripped away, the surface scorched to magma. It would orbit the eventual white dwarf remnant of the Sun for trillions of years as a lifeless cinder, a blackened tombstone marking where a vibrant world once existed. This is the end of our story, assuming we're fortunate. Because there's another ending that could happen at any moment without warning. An ending that emerges from the strange territory of quantum field theory. It's called false vacuum decay. High-energy physics suggests that the universe itself might not be in a truly stable state. The Higgs field, which gives mass to all fundamental particles, may exist in what's called a false vacuum. Think of a ball resting in a small depression on the side of a mountain instead of at the very bottom of the valley. It's stable for now, but it's not the lowest energy state possible. If a random quantum fluctuation somewhere in the cosmos were to push a tiny region of that field over the energy barrier, it would cascade down to the true vacuum state. This would create a bubble of space where the laws of physics are fundamentally different, and this bubble would expand outward in all directions at the speed of light. Inside the bubble, the properties of particles change. The mass of electrons might be different. The strength of the electromagnetic force might shift. Chemistry as we know it becomes impossible. Atoms cannot form. It would be a wave of absolute annihilation. And because it travels at the speed of light, there would be no warning whatsoever. No flash of light announcing its arrival. No time to say goodbye. The bubble simply arrives and reality ends. But suppose the universe doesn't destroy itself through vacuum decay. Suppose it simply continues, expanding and cooling according to the standard models of cosmology. It still faces an ending. In 100 trillion years, the last stars will burn out. The universe enters what cosmologists call the dark era. The sky, and in this final emptiness, we encounter perhaps the most disturbing philosophical paradox of all, the Boltzmann brain. The logic is simple and terrifying. In an infinite amount of time, even the most improbable events will eventually occur through random quantum fluctuations. And it is statistically far more likely for a single disembodied brain to spontaneously fluctuate into existence, complete with a full set of false memories of a life and a universe that never happened, than it is for an entire complex ordered universe like ours to arise naturally. Which means, statistically speaking, you are more likely to be a Boltzmann brain, a fleeting phantom consciousness that appeared 1 second ago in the void and will dissolve back into nothingness in the next, than you are to be a real biological entity in a real universe. This entire history, this entire story, might be nothing more than a random hallucination occurring in the final, infinite darkness. Conclusion. From the quiet demographic decline already beginning in our cities, to the artificial intelligences we are building in our laboratories, from the slow weathering of our monuments to the fiery consumption of our planet by its parent star, from the heat death of the universe to the unsettling possibility that none of this is even real. This is the map of all possible endings, a probability distribution that stretches from this present moment to the end of time itself. And what it reveals, with stark clarity, is that we are standing at the most critical juncture in this entire vast timeline. The next 100 years matter more than all the billions of years that might follow. This is the bottleneck, the time of perils. This century determines everything. It determines whether we remain a fragile, planet-bound species destined to die here, whether in decades or in eons, or whether we can navigate the gauntlet and become something more. Something that can spread beyond this single world, establish footholds across the solar system, perhaps even reach other stars. Something that might preserve consciousness and meaning until the final stars burn out. The universe is vast and old and silent. The silence may be the most important clue we have. It suggests that the leap from clever animal to sustainable spacefaring civilization is extraordinarily difficult. Perhaps no one has ever made it. Perhaps the filter ahead of us is insurmountable. But the fact remains that for now, in this brief window, the choice is still ours to make.